In telecommunications and professional audio, a balanced line or balanced signal pair is a transmission line consisting of two conductors of the same type, each of which have equal impedances along their lengths and equal impedances to ground and to other circuits. The chief advantage of the balanced line format is good rejection of external noise when fed to a differential amplifier. Common forms of balanced line are twin lead, used for radio frequency signals, and twisted pair, used for lower frequencies. They are to be contrasted to unbalanced lines, such as coaxial cable, which is designed to have its return conductor connected to ground, or circuits whose return conductor actually is ground. Balanced and unbalanced circuits can be interconnected using a transformer called a balun. Circuits driving balanced lines must themselves be balanced to maintain the benefits of balance. This may be achieved by transformer coupling or by merely balancing the impedance in each conductor. Lines carrying symmetric signals are often incorrectly referred to as balanced, but this is actually differential signaling. Balanced lines and differential signaling are often used together, but they are not the same thing. Differential signaling does not make a line balanced, nor does noise rejection in balanced cables require differential signaling. Explanation: transmission of a signal over a balanced line reduces the influence of noise or interference due to external stray electric fields. Any external signal sources tend to induce only a common mode signal on the line, and the balanced impedances to ground minimizes differential pickup due to stray electric fields. The conductors are sometimes twisted together to ensure that each conductor is equally exposed to any external magnetic fields that could induce unwanted noise. Some balanced lines also have electromagnetic shielding to reduce the amount of noise introduced. A balanced line allows a differential receiver to reduce the noise on a connection by rejecting common mode interference. The lines have the same impedance to ground, so the interfering fields or currents induce the same voltage in both wires. Since the receiver responds only to the difference between the wires, it is not influenced by the induced noise voltage. If twisted pair becomes unbalanced, for example due to insulation failure, noise will be induced. Examples of twisted pairs include Category 5 cable. Compared to unbalanced circuits, balanced lines reduce the amount of noise per distance, allowing a longer cable run to be practical. This is because electromagnetic interference will affect both signals the same way. Similarities between the two signals are automatically removed at the end of the transmission path when one signal is subtracted from the other. Telephone systems: the first application for balanced lines was for telephone lines. Interference that was of little consequence on a telegraph system could be very disturbing for a telephone user. The initial format was to take two single-wire unbalanced telegraph lines and use them as a pair. This proved insufficient, however, with the growth of electric power transmission which tended to use the same routes. A telephone line running alongside a power line for many miles will inevitably have more interference induced in one leg than the other, since one of them will be nearer to the power line. This issue was addressed by swapping the positions of the two legs every few hundred yards with a crossover, thus ensuring that both legs had equal interference induced and allowing common mode rejection to do its work. As the telephone system grew, it became preferable to use cable rather than open wires to save space, and also to avoid poor performance during bad weather. The cable construction used for balanced telephone cables was twisted pair, however, this did not become widespread until repeater amplifiers became available. For an unamplified telephone line, a twisted pair cable could only manage a maximum distance of 30 km. Open wires, on the other hand, with their lower capacitance had been used for enormous distances. The longest was the 1500 km from New York to Chicago, built in 1893. Loading coils were used to improve the distance achievable with cable, but the problem was not finally overcome until amplifiers started to be installed in 1912. Twisted pair balanced lines are still widely used for the telephone subscriber's local end. Telephone trunk lines, and especially frequency division multiplexing carrier systems, are usually 4-wire circuits rather than 2-wire circuits and require a different kind of cable. This format requires the conductors to be arranged in two pairs, one pair for the sending signal and the other for the return signal. The greatest source of interference on this kind of transmission is usually the crosstalk between the go and return circuits themselves. The most common cable format is star-quad, where the diagonally opposite conductors form the pairs. This geometry gives maximum common mode rejection between the two pairs. An alternative format is DM-quad, which consists of two twisted pairs with the twisting at different pitches. Audio systems. An example of balanced lines is the connection of microphones to a mixer in professional systems. Classically, both dynamic and condenser microphones use transformers to provide a differential mode signal. While transformers are still used in the large majority of modern dynamic microphones, more recent condenser microphones are more likely to use electronic drive circuitry. Each leg, irrespective of any signal, should have an identical impedance to ground. Pair cable is used to maintain the balanced impedances, and close twisting of the cores ensures that any interference is common to both conductors. Providing that the receiving end does not disturb the line balance, and is able to ignore common mode signals, and can extract differential ones, then the system will have excellent immunity to induced interference. Typical professional audio sources, such as microphones, have 3-pin XLR connectors. One is the shield or chassis ground, while the other two are signal connections. These signal wires carry two copies of the same signal, but with opposite polarity. Standard, and EIA standard or S297A, suggest that the pin that carries the positive signal that results from a positive air pressure on a transducer will be deemed hot. Pin 2 has been designated as the hot pin, and that designation serves useful for keeping a consistent polarity in the rest of the system. Since these conductors travel the same path from source to destination, the assumption is that any interference is induced upon both conductors equally. The appliance receiving the signals compares the difference between the two signals, allowing the appliance to ignore any induced electrical noise. Any induced noise would be present in equal amounts and in identical polarity on each of the balanced signal conductors, so the two sign ALSA unregistered trademark difference from each other would be unchanged. The successful rejection of induced noise from the desired signal depends in part on the balanced signal conductors receiving the same amount and type of interference. This typically leads to twisted, braided, or co-jacketed cables for use in balanced signal transmission. Balanced and differential. Most explanations of balanced lines assume symmetric signals, but this is an unfortunate confusion. Signal symmetry and balanced lines are quite independent of each other. Essential in a balanced line is matched impedances in the driver, line and receiver. These conditions ensure that external noise affects each leg of the differential line equally and thus appears as a common mode signal that is removed by the receiver. There are balanced drive circuits that have excellent common mode impedance matching between legs, but do not provide symmetric signals. Symmetric differential signals exist to prevent interference to other circuits. The electromagnetic fields are cancelled out by the equal and opposite currents. But they are not necessary for interference rejection from other circuits. Baluns. To convert a signal from balanced to unbalanced requires a balun. For example, baluns can be used to send line-level audio or E-carrier level 1 signals over coaxial cable through 300 feet of Category 5 cable by using a pair of baluns at each end of the CAT5 run. The balun takes the unbalanced signal, and creates an inverted copy of that signal. It then sends these two signals across the CAT5 cable as a balanced signal. Upon reception at the other end, the balun takes the difference of the two signals, thus removing any noise picked up along the way and recreating the unbalanced signal. A once common application of a radio frequency balun was found at the antenna terminals of a television receiver. Typically a 300-ohm balanced twin-lead antenna input could only be connected to a coaxial cable from a cable TV system through a balun. Characteristic impedance. The characteristic impedance of a transmission line is an important parameter at higher frequencies of operation. For a parallel two-wire transmission line, whereas half the distance between the wire centers is the wire radius and r respectively the permeability and permittivity of the surrounding medium. a commonly used approximation that is valid when the wire separation is much larger than the wire radius and in the absence of magnetic materials is. Where is the relative permittivity of the surrounding medium? Electric power lines. In electric power transmission, the three conductors used for three-phase power transmission are referred to as a balanced line since the instantaneous sum of the three line voltages is nominally zero. However, balance in this field is referring to the symmetry of the source and load. It has nothing to do with the impedance balance of the line itself, the sense of the meaning in telecommunications. For the transmission of single-phase electric power as used for railway electrification systems, two conductors are used to carry in-phase and out-of-phase voltages such that the line is balanced. Bipolar HVDC lines at which each pole is operated with the same voltage toward ground are also balanced lines. See also, differential pair, balanced transmission standards, RS-422, RS-485, low-voltage differential signaling, references. Hodderman, A.A., The Worldwide History of Telecommunications, Wiley IEEE, 2003. External links, balanced lines, phantom powering, grounding, and other arcane mysteries from Mackey.